Hi everybody, in today's video we're still going to be working with analyzing a function using its derivative, but unlike in the first video where we focused on the first derivative, today we're going to be focusing on the second derivative and seeing what that tells us about the original function. So we're going to be connecting a graph with its second derivative. So the big idea here is that the second derivative of a function tells us about the concavity of the original function. So this means we can tell when a function is concave up or concave down by looking at the sign of the second derivative. And we talked a little bit about concavity back when we were looking at whether our tangent line approximations were over or under estimates, but we're going to get into that more in this chapter. So concave up, as far as the picture, looks like this. We say it looks like a cup or it would hold water. And we say that a function is concave up because f double prime of x is greater than 0. So this should say concave up. So whenever our second derivative is greater than 0, we're concave up. And you'll notice for the second derivative, now we're not inclusive anymore. These are going to be open intervals. Concave down, on the other hand, looks like this. We say it's a frown. And we say a function is, this should say concave down. A function is concave down. When we're justifying it, it's because f double prime of x is less than 0. Now, the other new important term for today is what's called points of inflection. And points of inflection are places where the concavity changes. So we could change from concave up to concave down or concave down to concave up. And when we're justifying this, there's two things we need to say. So a function has a point of inflection because f double prime of x equals 0, I'm going to say or does not exist. And we also have to show that f double prime of x changes sign. So for a point of inflection, it's not enough for the second derivative to be 0 or does not exist. It has to be that value, and the second derivative has to change sign, either from positive to negative or negative to positive. So let's look at a couple examples on a graph here. So when we're doing this work, and I've mentioned this before, the most important thing is to be really clear about the graph that you're looking at. So in this case, it's the graph of f of x, so our original function. So again, we're talking about three things here. We have concave up, concave down, and then points of inflection. So let's look at concave up. So now, because we're looking at our original graph, we're just looking for kind of what we sketched up here, where it looks like a cup or would hold water. And here we can see that that's going to be over this interval here. These are going to be open intervals, so we could say that's going to be from pi to, looks like 2 pi there. So from pi to 2 pi, we're concave up. Concave down is where we've got our frown. And so in our case, that's going to be from 0 to pi. Now, in terms of point of inflection, where we changed from concave down to concave up is going to be at this point here. So we would say we have a point of inflection at x equals pi. So that's how we do this from the original graph. Now, in the second example, notice we're looking at f prime of x here. So we have to be careful in terms of how we look at this. Sorry, I'm going to go back and highlight this real quick. All right, so now we have f prime of x. We're still looking for the same three things. I'm going to put it down here. Still looking for where we're concave up, concave down, and any points of inflection. So let's look at concave up. We said we're going to be concave up wherever f double prime of x is greater than 0. So if I have a graph of f prime, f double prime is going to be the slope of f prime of x. So if I'm looking for my second derivative to be positive, that's going to be wherever f prime has a positive slope, so it's going to be over this interval here. So again, now I'm looking at the derivative of this function, but I can still see my original function f is concave up from pi to 2 pi. And again, remember we're talking about the original function here. F of x is concave up from pi to 2 pi. For concave down, it's wherever my second derivative is less than 0, so I'm looking for a negative slope for f prime, which is going to be over this interval here. So we would say from 0 to pi. All right, so now for point of inflection, we said that's where the second derivative is 0 or doesn't exist, and where f double prime of x changes sign. So my slope of f prime is going to be equal to 0 down here where I'm going to have a horizontal tangent, and I can see at that point the slope of f prime changed from negative to positive, so we do have a point of inflection at x equals pi. All right, so let's go ahead and look at a few more examples. All right, so again, we're starting off here looking at the graph of f of x. So this is our original function. So I'm going to start with concave up here, looking for where this is shaped like a cup. Now here we have to do a little bit of estimating. So this part I can see is going to be concave down, and then it switches to concave up. So I'm going to estimate that somewhere about in the middle there it's going to change. So concave up, we can estimate that to be negative 0.5, and then it's going to stay concave up. Because of that arrow, we're going to go till infinity. Concave down, we can see that happening here. So we would say from negative infinity to negative 0.5. Now, where I have that change in concavity, that's where I have my point of inflection, x equals negative 0.5. So again, that was the graph of our original function. Now let's look at a graph of the derivative. And hopefully, if we're doing this right, these should match. This is the derivative of this function, so I should get the same information about concavity. So f double prime of x, again, for concave up, we said that's where the slope of f prime is positive. So if I look at f prime, since that's what my graph is, I can see I have a positive slope over this interval. And so if we estimate this value here, again, we're looking at that negative 0.5, and that goes till infinity. For concave down, I'm looking for my second derivative less than 0, so that's going to be where the slope of f prime is negative. And we can see pretty clearly from here that that's going to happen over this interval. So for concave down, we're going to be from negative infinity to negative 0.5. And again, where concavity changed here, my slope changed from negative to positive, we're going to have a point of inflection at that point. Now, just like we did the other day, we're going to have to find this information from an equation for the function as well. So that's what we're going to do next. So if I'm looking for information on concavity and points of inflection, I know I'm going to have to work with the second derivative. So I'm going to find that first. So my f prime of x is 6x squared plus 6x, which means that f double prime of x equals 12x plus 6. And I'm going to start by setting that equal to 0. So when I do that, I'm going to get 12x equals negative 6. So x equals negative 6 over 12 or negative 1/2. Now, the important thing to note here, we found out where our second derivative is equal to 0. Right now, we don't actually know yet that we have a point of inflection. What I'm going to say is that this is a possible point of inflection. We have to actually do the analysis to make sure that there's a sign change at that point before we can call it a point of inflection. So that's what we're going to do now. I'm going to make myself a table for f double prime of x. And let's see, we've got from negative infinity to infinity, and my possible point is negative 1/2. So I'm going to pick something smaller than negative 1/2. So let's say negative 1. If I plug that in, I get negative 12 plus 6, which means I'm going to be negative on that interval. If I plug in something bigger than negative 1/2, I'm going to go easy and make that 0. This is going to be positive. So I can see from my sign where f double prime of x is negative, that means I'm going to be concave down. Where it's positive, I'm going to be concave up. So now we can translate that into our interval notation. So concave up, we're going to be from negative 0.5 to infinity. Concave down is negative infinity to negative 1/2. And then we can see, because we had a sign change for the second derivative at x equals negative 1/2, that's going to be our point of inflection. So we have three different representations for the same function. We have the equation, a graph of the original up here, and then the graph of the derivative, but we should be able to analyze all three to get this information about the concavity of the function. All right, so now we're going to go through some practice here, look at some multiple choice questions, and then some more examples analyzing functions and graphs. So let's go ahead to number 4. So here we have a multiple choice question. This could be pretty typical of what would be on the AP exam. It says if y is a function of x such that y prime is greater than 0 for all x and y double prime is less than 0 for all x, which of the following could be a part of the graph of y equals f of x? So here's where we have to be able to translate what we know about derivatives and turn it into information about the original function. So the first thing they're telling me is that y prime is greater than 0 for all x. That's telling me that y is increasing. If the first derivative is always positive, it means y is always increasing. Next, they're telling me that the second derivative is less than 0. That means y must be concave down. So now I've got information about the original function that I can use to pick the correct graph. So first I'm going to go through and knock out anything that's not strictly increasing. It says for all x, so that means it has to always be increasing. So here we've got increasing. This is always increasing. C I can see is decreasing. So we're going to X that out. D starts off increasing, but then starts decreasing. But we know it's always increasing because it was for all x. And then E we're not quite sure about yet because that's increasing as well. So now we need to look at the concavity. It says y needs to be concave down. So A I can see is concave up, so that choice won't work. B looks good, we're concave down. I just want to check my other options. Here we start off concave up, but then change to concave down. Oh, that one was already knocked out anyway. Let's look at E. Starts off again concave up and then switches to concave down, so that won't work, meaning our choice has to be B. All right, next one, again, very typical of what will show up on the multiple choice section of the exam. It gives us the graph of a twice differentiable function. So this is, in other words, our original graph f. And it's asking about which of the following is true. And you can see we're asked to compare three quantities. We've got f of 1, f prime of 1, and f double prime of 1. And we basically have to order them in relative size. So let's see what we know from the graph. First of all, I can see if this is f, that f of 1 is just equal to 0, right? And we can get that from this point right here. So that's how I know. It's just that point on the graph. Now, f prime of 1, we know that f prime of 1, that has to do with the slope of f. In our case, the slope of f is negative. So that means f prime of 1 must be less than 0. Lastly, f double prime of 1. What they're asking is about the concavity of f at x equals 1. Since this is looking like half of that cup shape that would hold water, we would say this is concave up at x equals 1, which means my second derivative at 1 is greater than 0. So now if I were going to order these, I know the smallest is f prime of 1, f of 1's in the middle, and then my largest is f double prime of 1. Again, we don't care about the actual values, just the relative magnitude. So it looks like in this case the answer is going to be C. All right, let's go ahead and do, I think we'll just do one more and then we'll save the last example for when we're in class. Actually, you know what, I'm going to end it here because it gets into kind of pulling everything together in the next example. So we'll walk through that all together in class so that I can address any questions that you have. So just make sure you've got good complete notes on everything we've talked through so far, and we'll pull together day 1 and day 2 when we're all back in class. All right, thanks. See you then.